Hey guys, how's it going? This is Siri and I'm back with another PyTorch video. And in this video, we're going to be actually wrapping up our discussion on this whole learning process. It was quite a journey. And we are, just to recap what we've been talking about in the past, like many videos, we've been talking about the whole machine learning process, what that entails, what inputs and outputs are, and we just started off with a simple linear mathematical model, and we tried implementing it manually. And the reason I chose to do that is because once we, really understand what's going on behind the scenes, in a simple example, and what we're actually trying to do, it'll be easier to implement that in PyTorch, because then we're just talking about how we do it in PyTorch. We're not talking about like why we do it. And I mean, like, we will, but like it'll be a lot more, it'll be easier to understand once we've like gone through an example like this. So we went through a linear mathematical model. We talked about what it means to define a model, a loss function, initialize parameters. What, like, the whole idea is to change, update, and estimate W and B, which are our weights and biases, so that our loss reaches a minimum. How do we do that? We use derivatives. How do derivatives play a role in it? Well, we have to take the derivative of the loss with respect to each of our parameters, and and then learning rate, which scales that number down so that we're not updating it by an insanely large number. Normalization. And do we even need to, find a derivative for each of our parameters, especially if there might be millions of parameters in a neural network? Maybe not in just this like manual linear model that we've defined, but if we have hundreds and millions of parameters, PyTorch's autograd comes in handy. And, we talked about what it means to accumulate gradients and what we can do to stop that, what optimizers are, what are the different optimizers that PyTorch has to offer, what is an optimizer, what's an optimizer object, and that's where we left off, okay? And in this video, we're going to be talking about the training and testing datasets, okay? And it's still going to be based off our little example, and if you weren't there for that, well, we just, converted between like Celsius and Fahrenheit, assuming that we didn't know that it was Fahrenheit from the beginning, so we could, see the relationship between the inputs and the outputs. And now we're going to be talking about the training and testing data sets from our little, tensor that we've created at the beginning, which was TU for temperature unknown units, to temperatures TC, temperature in Celsius. But you don't need to, I would definitely recommend watching my previous videos if you want a bit of a refresher on what these different topics we've discussed in our little recap, or you want to know what they are in depth. I would definitely recommend watching those videos. But you don't need to know the entire example, like the specific example, to understand this video. So when we're trying to decide if we've done well in training our data and fitting our model to the data, which just means finding that best fit line in our linear example case. So did we find that best fit line that models our data, and when we pass in a new coordinate or like a new x value, can we get an accurate y value as an output? Can we get an accurate temperature as an output, and can we predict that accurately? That depends on how well your model has trained on your data, and that depends on how well, you have the best, like, whether you have the best slope and y-intercept or not, which is exactly what I said before. But, yeah, so if we're trying to decide whether we've done a good job with that or not, then we can do something called evaluate the training loss, right? If we want to know whether we've done a good job, we need to evaluate the loss, because the whole goal of this entire process is to minimize the loss. The loss being the difference between the the actual value, the actual output, and the predicted output. So you don't want the predicted output to be so far off from the actual output, because then you did a bad job predicting, right? You want it to be like relatively pretty close to each other, right? So we can evaluate the training loss and make sure that it's doing the things that it's supposed to be doing, which is decrease. But if it's not decreasing, right? What might have gone wrong? If the training loss isn't decreasing, what might have gone wrong? Well, you might have two possible things that could have gone wrong, and they are, like, the first one is maybe your model is too simple. Maybe, you're trying to predict data that should be an ellipse when graphed using a line. Like, a line is way too simple. Maybe if you have something very, very complicated and you're trying to predict and represent that data using a line, a y equals mx plus b line, and you think that that's the relationship between the input and the output. That's way too simple. You have way too few parameters. So once we start going outside the realm of just linear models, we're going to have to realize that there's so many different numbers that can impact, that come together in your tensor operations, that come together and impact the overall output. And these aren't just going to be the slope and the y-intercept, or the m and the b, or the w and the b. There are going to be so many different other numbers that impact the overall output, and those numbers are what we call parameters. Right? The slope and y-intercept are also parameters, except they're a part of a very simple case. If we have a neural network, then we're going to be starting to use the word parameters a lot, and we're still going to be using M and W and B, because there are, linear units and linear layers, but we'll get into that. We'll get into that later. So I just want to make sure that when I use the word parameters, they might not just be referring to the W and the B. Okay, so maybe your model is too simple. Okay. Right? Fewer parameters and not fitting data properly. Okay? Or maybe, the data just doesn't contain meaningful information. So we have useless information when training. Okay? And it doesn't tell you anything about your output. So when might that be the case? Well, I think I've talked about this weather app example, and you've developed something that can predict what the weather's like just based on a few parameters. But those few parameters aren't, temperature, humidity, and those sorts of meaningful information. What you have instead is, what brand of shoes are you wearing? What color shirt is it? Is it red? Is it blue? That's the information that you're collecting from the user to predict the weather. And that is useless information. That doesn't tell you anything about the output. And so when you wear a red shirt and your model is trained to think, oh, you're wearing a red shirt and you're wearing Nike shoes, then it must be raining, or it must be sunny. If you're not wearing any of these things, it must be cloudy, or it must be hailing or snowing or something like that. Okay, and that's just plain wrong, because you're basing your you're literally basing your argument on the wrong pieces of evidence, right? So you're basing your output on the wrong pieces of information. So that might be the case. And you might have another problem. Maybe your training loss is very, very small, so you're doing great on your training. But remember, when we talked about this originally, when we started talking about this whole, this whole learning process, we've discussed Kepler and how he, did the same sort of thing when coming up with his laws of planetary motion. He had data that, he had data that he used to come up with his mathematical model, but he also had a set of data that he could use to test his, his sort of hypothesis and not hypothesis, but test his model and whether this, this elliptical model really models and represents the data that he had. So you need a test, you need some sort of test data to make sure this is a new piece of information that you're passing in. So your model's all good and it's trained, and it thinks that it's x plus 2, but then when you pass in a new piece of information, it thinks that it's 6 when it should be 25, when this is what the actual model looks like, or something. So you need some test data, and so that's why you need test data. Okay, so need test data to, check out how your model, how your final, model does on the data, on the equation or whatever. So, okay, good. So, okay, what if it's fitting super well to the training data, and then, I think we went on a tangent here. Like I was saying originally, what if your model, predicts your training data super well? And then when I started talking about test data, we went into what test data actually is. So, if it does super well on your training data and it does poorly on your test data, what does that tell you? Well, if you search, best fit line, and you look at an image, and, you see this. This is your training data, okay? And your model thinks that, you go here and here. If you can see my mouse. If you can't, let me take a okay, 1 second. Okay, whatever. 1 second. Copy image. Okay, if you run it. Okay, can you, 1 second, let me bring up the drawing tool so you can see what's going on. Okay, so I pulled my drawing tool up. So what I'm saying is that if this is your training data, these dots represent your training data, and your model, comes up with, an equation or a mathematical expression that, models the data like this. Oh gosh, this is red. Okay, okay, hopefully you can tell the difference. Yeah, you should. It's a squiggly line. Okay. Okay, hopefully you get the point. Okay, your model thinks it's like this, okay? And each time it runs, okay, 100%, right? You get 100% accuracy, or 99% accuracy. You're doing wonderful. But this isn't generalized at all. This is a squiggly line, when in reality, this trend line that was drawn originally should have been used. Okay, oh, actually, I can change the color. Yeah, so... yeah, this is the crazy squiggly line that your model thought it was when it should have used that red line that we started out with, like this thing that I'm doing in blue. Okay? So when you get new data that actually can be represented by this trend line, and you use this squiggly line instead that doesn't represent the data at all, you're gonna get horrible accuracy, probably like 60, maybe not 60, but like 67% accuracy on your testing data. Okay? It's really bad. I mean, like, depending on the situation, right? And depending on the problem and the data, but, you know, if you're comparing it with 100% and you go down to 67%, you know, like, it can't generalize. Alright, so let me erase this. Or, actually, let me turn off the drawing tool. Okay, unfortunately, it got all erased. And yeah, okay, whatever. So yeah, it's overfitting. This is called overfitting. It's representing the training data way too well and can't generalize to the testing data. Okay, so that's what's going on here. And generalization is exactly what we are evaluating with the testing data. That's the whole purpose. We want it to be able to generalize, and it's not when it's overfitting. Okay, so, okay, great. So now let's talk about how we would split the data, now that we know what training and testing data are, and like the two situations where things might go wrong, actually three. Okay, so splitting the data is going to involve some shuffling. Okay, so you know, like how you shuffle a deck of cards. You know, similarly, we're gonna, you know, shuffle the indices of the entire data, and then put some of it for the training, some of it for testing. Okay, and let's say that we have okay, n samples. Okay, so these are our training samples, like pieces of data, individual pieces of data that we're using. And TU is like the temperature unknown, like I said. Shape 0. Shape just tells you, you know, the dimensions, and 0 refers to the rows. If we're looking at 2D data, which we are. So, yeah, so these are the number of rows, and nval for validation is probably going to be, you know, you usually set aside maybe like 20, 25 or 30% of your entire data to validation, right? We need a balance. We don't want to do 50-50. I mean, you could, but like, okay, you want to train accurately, but you also don't want to have a very small amount of validation, because then you're not gonna know whether your model's actually doing well or not. So yeah, okay, so 0.2 times n samples. Alright, so 20% goes to validation. Alright, and you know, shuffled indices. There's a nice little factory method that you can use. torch.randperm, random permutations. Okay, and you pass in the data, and it'll shuffle the indices for you. And when you want to create your train indices and your test indices, you can do shuffled indices and, you know, do up until nval. Okay, because that's where the training, that's where the testing starts, and training ends. And shuffled indices. Negative and val. Okay, so he's starting from the end and going all the way up until end val. Negative. Okay. So actually you're starting at the end and then you're going up until like wherever you stop here. Alright. Okay, so now you can call it test or validation. Okay, so train. Let's take a look at the train indices and test indices and val indices. Oh no. Okay, I guess I'm gonna have to run this again. I should have used another, I thought of using another Jupyter notebook, but, you know, it's nice to have everything in the same place so you can, you know, look back and actually use the data that we've defined. So if we want to use it for this long, then we're gonna have to import it as like a module, and you know, I just decided to keep it all in the same one. Okay, we're running all this. Don't see any errors. Oh great, I just okay, this is a markdown cell. Okay, good. Cool. So we have some tensors, and actually this should have been negative. So you go to the end. Okay, yeah, that's better. Okay, so this is tensor. This is your training indices and testing indices. Okay. And recall we had a tensor full of temperatures, so these are the indices or indexes that we're getting. So an interesting thing that we're doing here is we're actually passing in a tensor as an index. So it'll do it element-wise or like index-wise. So it's like a cool thing, right? Like when we, you know, when we deal with regular Python lists, what we're doing is like when we add them together, we concatenate them. But with tensors, you're actually doing an element-wise addition. So similarly, you know, when we're indexing using PyTorch tensors, we're doing the same thing here. Like we're doing this element-wise sort of indexing. So that's one cool thing I might not have mentioned that you can do with tensors. Okay, so now let's normalize them by just multiplying it by 0.1. If you don't know what that means, I would definitely recommend checking out one of my previous videos. But just to give you a high-level overview, you know, it has to do with the gradients like blowing up. And if you just want to standardize and normalize your inputs, that'll be best for like the overall training process. So yeah, TUN value and train TUN and val TUN, where the N stands for normalized. 0.1 times val tu. Why do I keep saying tc? Okay, this is tu because we're talking about the inputs, right? We want to normalize the inputs so that the gradients don't blow up. Okay, good. So let's run it. Let's define the training function. And let's copy, yeah, let's literally copy this, okay? We're just going to be making some edits to this. Okay, so n epochs, optimizer, params. So now we're going to be passing in our train tu, val tu, and train tc and test, or like val tc. Okay, so now originally we just had tu and tc. Now we're having train tu and val tu and train tc and val tc. Okay? So essentially the only change that you can see in the code is the change in nomenclature here. So we have train TP. But don't just think of it as a change in nomenclature. Think of it like, really understand why we're doing it, which I'm going to be going through now. Just wait a second. So now, instead of just loss, now we have train loss. Now, we're going to copy this, except now it's going to be val and val. Okay, so, and let's pass in train tu, train TP, and train TC. Train TP is just what we've defined here as the temperature predicted of the model. Training loss, train TP, train TC, val TP, val TU, and val TP. Okay, optimizer 0 grad, train loss backward. And I'll talk to you about, what we do with the training loss and why we don't do that with the testing. Okay. So let's return params, and we define params, right? Params we just defined as okay, yeah, we're just defining it as this. Keep that in mind. Yeah, I'm gonna be scrolling down now. Alright, and let's run it. And let's call the function. Let's call the training loop. Okay, so optimizer is equal to optimizer, params is equal to params. Now we're gonna have train tu. Tu is equal to train tun. Remember we defined that. And val tu is equal to val tun. Probably gonna have to delete this. Train tc is equal to train tc, and val tc is equal to val tc. Alright? Okay, train tun. Okay, yeah, that's much better, because the values that we were getting before were really high, and yeah, I was kind of confused for a second, because they were like 1,000. The losses were 1,000. Okay, this seems much more reasonable considering the data that we have. And you see the training loss, 2.8 and 3.2. So you see that, you know, there's some slight overfitting that's going on. I mean, I guess you can't say that every single time the testing loss is greater than the training, because, you know, there might be some other factors that play into that, but, like, generally, if the training loss is considerably lower than the validation loss, then you can say that it's an overfitting case and that your model is training way too much to your training data. Okay, and yeah, we'll have another video to talk about, to like really wrap up this discussion, because I think we're going too long anyway. But yeah, definitely the next video is definitely going to be the last one on this topic. I hope you learned something new today about like how to actually implement it, what training and testing data is, and what it is in PyTorch, and you know, speaking of it in terms and in the context of you know, the different parameters that we've been learning about, and you know, the fact that maybe the model is too simple or there's useless information. Hopefully it's becoming a lot more clear to you right now. But yeah, I think the next video will really clear things up. I didn't actually get to talk about the training and testing loss as I thought I would, and I said I would, but I'm just going to be pushing that to the next video, so you can look forward to that then. Alright, thank you so much for listening, and I hope you learned something new today, and don't forget to like, comment, and subscribe.